Okay, so in this video we want to discuss the ideas of continuity, differentiability, and graphs of gradient functions. So we'll start off by talking about continuity. Now continuity has a quite nice, neat, informal definition which we'll talk about in a second. But formally a function, f of x, is continuous at a point with coordinates of a and f of a, so x coordinate of a, y coordinate f of a, if these three things all exist and are all equal to each other. So the limit as x approaches a from below, I'll discuss that in a second, of f of x, is equal to f at a, so the actual value of the function at a, which is also equal to the limit as x approaches a from above of the function. Okay, so let's have a quick discussion about what that means and when that therefore wouldn't happen. So let's just think about some sort of very simple smooth graph, okay? Let's say this point here, so this is y equals f of x. Let's say this point here has an x coordinate of a, and so therefore has a y coordinate of f of a. Okay, so the idea of the left-hand side here, so the limit as x approaches a, and that little negative in the subscript, in the superscript, means that we're looking at the limit of the function, the limiting value of the function, as x gets closer and closer to a, but as it does so from below a. Okay, so as x approaches a from below. Okay, so as we travel along the function from smaller x values than a towards a, the limiting value, it must exist, it must actually limit to a value, and it does, it limits to, the value of the function limits to f of a. Okay, so if that limiting value is equal to f of a, and similarly the one on the right hand side is the limit as x approaches a from above of the function. So as x gets closer and closer and closer to a, but from higher x values, the limit of the function should also be f at a. Okay, so this sort of skewed looking parabola shape that I've drawn, this function would be continuous anywhere. You could pick any point on this graph and the function exists at that point, it has a y value at that point, and the limiting value of the function as I approach that point from both above and below, not vertically above and below, from x values above and below, also approaches f at a. Okay, so that would be an example of a continuous function. So let's then think about, okay, well, when might a function not be continuous? Let me just remove that for a second. Okay, so let's think about what would happen, for example, if, well, the simplest one, if this one wasn't true. If the limiting value as I approached from above and below wasn't equal to f at a. And that would be a very simple, that could be something as simple as, well actually there's a couple of things. That would be as simple as, we might have a curve with a hole in it, okay, where the domain of the function for whatever reason is real numbers excluding a. Now in that instance, the left-hand side, the limit as we approach a from below, certainly does, so we would still, that point would still have coordinates f at a. The limit as we would approach a from below certainly would approach f at a. The limit as x approaches a from below, oh sorry, not a negative one, just from below, of f of x would indeed be f at a, okay? And the limit as x approaches a from above would also be f at a. But f at a doesn't exist. Well, sorry, f at a does, but the function is not defined when x equals a. We could, well no, it doesn't actually. So f at a doesn't exist. So it would be possible for the two limits to exist, but the actual value of the function at that point doesn't exist. The other thing that could happen on a similar vein would be if we had a function, for example, let's have a x equals 2 or no, let's make it x equals a to be consistent, okay? So let's say we had a truncus, okay? So in this instance, the limit as x approaches a from below of f of x is infinity, okay? The limit as x approaches a from above is also infinity, so those two things exist and are equal to each other, but f of a, again, is undefined. So f of a might be undefined if we have an asymptote at that point, if we have a hole in the graph at that point, like I drew in the previous example. And in those instances, we would say that the graph is discontinuous at x equals a. It is not continuous when x equals a. Okay. Obviously, we could also have a truncus, sorry, not a truncus, we just drew a truncus, a hyperbola. And in that instance, the limit as x approaches a from above of f of x would be negative infinity, and so lots of issues. Those two things actually don't equal each other, and the value of the function at a also doesn't exist, so it would certainly be discontinuous. The other thing that might be happening in terms of continuity might be something like, let's say we've again got a, let's say we've again got a curve. So let's say we've got a hybrid function where they're joining at a. So in this instance, what we would have is the value of the function at a would be this value. That's f at a. Okay, it's not this value. It doesn't exist at that point. So in this instance, the limit as x approaches a from below of f of x would be f of a. F of a does exist, but the issue here is that the limit as x approaches a from above of f of x doesn't equal f of a. It equals whatever that value is. Okay, and so therefore this one's the issue here, the one on the right hand side. And obviously we could have hybrid functions with the point, so if that point wasn't included and that point was, the limit from above would be okay, but the limit from below wouldn't. The other one I want to just have a quick think about would be if you had a hybrid function, while we're thinking about hybrid functions, where the graph did actually meet at that point. Okay, so in this instance, you've got, okay, f of a exists, so the middle one is a tick, because that's an included point on the graph. The limit as x approaches a from below is f of a, and the limit as x approaches a from above is also f of a. And so in that case, it would be continuous. Okay, so loosely, informally, a function is continuous at a point if we can draw the graph through that point without lifting our pen. Okay, so nice smooth parabola, continuous everywhere. This graph here, also continuous everywhere. I don't have to lift my pen at this point. If, however, this was a not included point, I'd have to draw my pen, lift my pen at that point, and then continue to draw from there. Again, if you had a function with a hole in it, you'd have the same issue. You have to lift your pen over that little hole. If you have a function with an asymptote, you have the same issue. You have to lift your pen off the paper to be able to continue to draw the graph. So essentially, if you can draw the graph without needing to lift your pen at any point, it is continuous at all of those points. Okay, any point where you must lift the pen to be able to continue on and draw the graph, that would be a point of discontinuity. The function is discontinuous at that point. Okay, so let's have a look at these graphs here. So example 1, state the value or values of x for which the following functions are continuous. So we want to state the range of values where the functions are continuous. Okay, so example 1, we've clearly got a discontinuity when x equals 1. So this would be continuous for x is an element of all the real numbers except for at 1. That would be a point where I would need to lift my pen. In this instance, the limit as x approaches 1 of f of x is equal to f of 1, but it's not equal to the limit as x approaches 1 from above of f of x, because that would be equal to this value here. Okay, so they're not equal. So we fail with the right-hand side of the statement about continuity. This one here, the parabola. Obviously, again, we've got a discontinuity with the hole in the graph when x equals 2. So we would say this is continuous for x is an element of any real number as long as it's not 2. And the issue here is that f at 2 doesn't exist. So it can't be continuous at 2. The limit as we approach from above and below is the same, but the graph doesn't actually, the function doesn't actually exist at that point. Okay, this third one here, we've got our hyperbola. We've sort of discussed this one. So again, here it would be continuous everywhere except at that asymptote where we would need to lift our pen to continue to draw. So this would be continuous for x. It's an element of all the real numbers except for -1. And again, the issue, lots of issues here actually. F at -1 is undefined, so we fail that. And equally the limit from the two different directions. So the limit as x approaches -1 from below of f of x doesn't equal the limit as x approaches -1 from above of f of x. Okay, this one would be positive infinity and this one would be negative infinity, so they're not equal to each other. So a couple of issues with continuity there in terms of the formal definition. Now this one's an interesting one, and here obviously we can draw this graph completely without lifting our pen. The question is, what about here? Now in terms of where this is continuous, the question is, can we say that the graph is continuous when x equals 2? And we don't have enough information to be able to say that. Okay, so in this instance we can certainly say the limit as x approaches 2 from below of f of x is equal, is equal to f at 2. Okay, so it's going to be, let's say that's 8. Okay, but the issue here is we don't know whether that's also equal to the limit as x approaches 2 from above, because the graph stops at that point. So we can't possibly say that it's continuous at that point, at x equals 2, because we can't know, what happens after here. We can't know whether the graph continues on and is joined up. We can't know whether the graph, is a hybrid and something else happens here. We can't know what happens from here, whether it just doesn't exist at all. Then there is no limit after that, and therefore it can't possibly be equal to f of 2. So we would say that this is continuous for x is an element of, so everything from negative infinity all the way up to 2, but not including 2. Okay, so let's be clear about that, because the domain of this function would be negative infinity to 2 including 2, but we can't say that we're continuous at that endpoint. So places where we're likely to see discontinuities. Holes in graphs, so just little empty circles, asymptotes, endpoints. Those are probably the key features we're going to see where we would say the graph is not continuous. So in terms of answering the questions, these 4 sets of x values. So as I said, informally, if f of x can be drawn through the point without break, so without needing to lift your pen off the paper, then f of x is continuous at that point. Okay, let's extend that idea onto differentiability. So differentiability is about whether the graph, whether we can calculate the derivative at that point, which is about whether gradient is defined at that point. Okay, so there are 2 things that need to be true for a function to be differentiable at a point. Say, for example, the point when x equals a. It has to be continuous. We've already looked at how we know things are continuous, and smooth. Okay, so in terms of the sort of continuity things that we've looked at, we've seen that if we have, if we have holes in graphs, we would have discontinuity, therefore graph wouldn't be differentiable at that point as well. If we have asymptotes, we have issues with continuity, therefore graph wouldn't be differentiable at the asymptote. If the graph doesn't even exist at that point, you can't possibly think about gradient. We've also seen that we can have hybrid functions. So if we've got a discontinuity there, the graph wouldn't be differentiable at that point. The difference here is what we have seen is if the graph did that, the graph is continuous at that point. But in this instance, it's not smooth. So you also want that sense that the gradient as you come into the graph from both sides is the same. Okay, so the limiting value of the gradient is the same as well. Okay, so we're getting a nice smooth point. So for example, you could create a hybrid function, parabola and then a line, where they do join smoothly and hence are differentiable there by making sure that the line has the same gradient as the parabola at that point. But the minute the line has a slightly different gradient to the parabola at that point, you've now got a not smooth join, and therefore the function is not differentiable at that particular point. You should be able to think about too, can I draw a tangent at the point? That might help you think about, is it differentiable there? So if you were trying to draw a tangent here, well, you know, do you draw it there? Do you draw it like that? Do you draw it like that? It's not a point at which we can calculate gradient. So as it says here, if a function is differentiable at a point, it means that its derivative exists at that point. Functions are not differentiable where there are discontinuities. We've just had a look through those different discontinuities, and where the graph is not smooth. That is where there are sharp corners or cusps, which is what we were looking at in this particular example over here. The other thing is that functions are also not differentiable at points where the tangent is vertical. So let's think about, we have met a graph type where this happens. If we think about f of x equals x to the power of a third, remember that's the inverse function of x cubed. So that is the sideways cubic. So at this point, when x equals 0, we get a vertical tangent. And so therefore we know the gradient of a vertical line is undefined, and therefore the graph would not be differentiable at that point. Okay. It should also be noted that functions are not differentiable at their endpoints, and that's just because they're not continuous at their endpoints, so you can't calculate gradient at an endpoint. Okay, let's answer these questions. Apologies, these graphs have printed a little blurry, but we can see what we need. So state the values of x for which the following functions are differentiable. Okay, so they're going to be differentiable wherever they are continuous and smooth. Okay, not at endpoints though. So in this case, we would be differentiable for x as an element of, so from -1 up to 5. So again, we're not differentiable at 5 because it's not technically continuous at 5 because we don't know what's happening after here. Again, thinking about if I asked you to draw a tangent when x equals 5, well, you know, we don't know what's going to happen because we don't know what's happening after here. Okay. Okay, so the domain of that function, it will be worth noting, is -1 to 5, including 5, but the function is not differentiable at 5. Okay, the second graph there, we're thinking about where that function is differentiable. That function is going to be differentiable everywhere except here where we've got a sharp corner. We've got two lines with different gradients meeting at that point, and therefore deciding what the gradient actually is at that point is going to be very difficult, or impossible actually. So this function is differentiable for all real numbers except when x is equal to -3. And then this one here, same thing, we've got a discontinuity, and so it's going to be differentiable for all the real numbers except for at that point of discontinuity, so except for at 1. Whereas again, the domain of that function would be R, but it's not differentiable over its entire domain because of the discontinuity. Okay, sorry, apologies about the keyboard. So then we want to keep those ideas in mind, particularly the idea about differentiability when we sketch the graph of a gradient function. Okay, and we want to be able to do this even if we don't know the equation of the original function. Okay, so this isn't necessarily about drawing a perfectly precise graph, but this is about making sure we draw a gradient function that at least matches what we can see. Okay, so the first thing I'm identifying in part A is that my function is a quadratic function. Okay, and hopefully we know that when we differentiate a quadratic function, we get a linear function. When they're polynomial functions, the degree of the polynomial is reduced by 1 when we differentiate. So when I draw the graph of the gradient function, it's going to be a linear function. The next thing I'm probably going to look for is to think about key points. So for example, I know when x equals a, the gradient is 0. So let's be clear about when we're drawing the gradient function, the y-axis now becomes not y, but gradient. Okay, so I know when x equals a, gradient equals 0, so my gradient function goes through the point a0. Okay, then if we think about before that point, we know that our original function has negative gradient. So thinking about the fact that my vertical axis is gradient, I get 0 gradient, sorry, zero gradient at the x-axis, I get positive gradient up here, and we get negative gradient down here. So if my gradient function, if my gradient is negative when x is less than a, my gradient function must be below the x-axis when x is less than a. And then it's going to be positive after that, so it goes above the x-axis after that point. Now, we don't have enough information to work out precisely what the gradient of the gradient function is. I'm just going to make sure I draw a straight line that starts below and finishes above. It doesn't matter if your line is this way, it doesn't matter. I'm trying not to meet it at that point deliberately because I don't think it will, and we don't know that. So, but you might draw it, flatter and meet it down here. Now, the next thing to think about is at this endpoint, the gradient is not defined. So when x equals c, and we don't know what the y value of that will be, the gradient value of that will be, but when x equals c, we should have a hollow circle because the gradient is not defined. So that comes back to the differentiability. We know this graph is differentiable from negative infinity up to c, but not including c, and so therefore that should be the domain of my gradient graph when I sketch it. Now again, I don't have enough information to know about the steepness of my gradient function. I don't have enough information to know about the y-intercept of my gradient function, but I do know that this is a straight line with positive gradient that has an x-intercept at a0 and a not included endpoint at c. Okay, so those things all need to be reflected in what I draw. Okay, so part B, again, we want to sketch the gradient function. So we're now thinking about our vertical axis as representing gradient. So when x equals something, what's happening with the gradient? So again, key points to start with would be places where you know the gradient is 0. So I know the gradient is going to be 0 at that turning point where x equals a, okay? And I also know it's going to be 0 at that turning point where x equals c. The other thing I'm noticing is that my original function looks like it's probably a cubic function, and so therefore the gradient of that will be a quadratic function. So I'm looking to draw a parabola with these two x-intercepts, okay? And then I want to think about, okay, is it going to be a parabola that goes this way, or is it going to be a parabola that goes this way? And that's about thinking about the gradient. So I know when x is less than when x is less than a, which is this point, which is this point here, a0, I know the gradient is positive. So that means my gradient graph must be above the x-axis. When x is between a and c, which is this other point, when x is between a and c, I know the gradient is negative. So my gradient graph must be below the x-axis in between those 2 points. And then I know when x is bigger than c, my gradient is positive again. Okay, and so my gradient graph will be above the x-axis again. So a parabola that needs to be above the x-axis when x is less than a, below the x-axis when x is between a and c, and above the x-axis after that. Again, I don't have enough information to know the steepness of that parabola, to know exactly where the, in terms of the y-coordinate of the turning point, exactly where that would be. But I should have definitely a parabola drawn. I certainly don't know the y-intercept of that gradient graph, but I certainly should have a parabola drawn this way up, a happy face parabola, with x-intercepts at a and at c, and that information should be reflected in my sketch. Okay, so part C, here we've got a hybrid function. So we've got a linear function. Now linear functions have constant gradient. Now if I had 2 points on here, I could actually work out exactly what that constant gradient is. The only thing I do know about it is that it's clearly a negative constant value, and so therefore it's going to have to be somewhere down here, okay? So I know that I'm going to have some sort of constant, my gradient's going to be some sort of constant negative value. So remembering again, we're looking at drawing the graph, thinking about the vertical axis as being equal to the gradient. And then at x equals a, I've got a discontinuity, so my graph isn't differentiable here. So the graph shouldn't exist at that point. Okay, so that's going to have an x value of a. We don't know its y value. We only know that it will be, or its gradient value. We only know that it will be negative. Okay, and then after that, we have a parabola. Okay, so the gradient function will be a linear graph, but a linear graph with a gradient, not a horizontal graph like what I've just drawn on the left. We can see that we've got 0 gradient when x equals d. So it's definitely going to cross the x-axis at d. Okay, and we can see that we have positive gradient before that and negative gradient after that. Okay, so again, I don't know what the steepness of this line is going to be, but it's definitely going down, and it's again going to have a not included endpoint at x equals a. Because the graph is not differentiable at x equals a, neither of those endpoints should be included. It doesn't matter that this endpoint's included. Remember, discontinuous at an endpoint, so not differentiable at the endpoint. So again, getting the shape right, putting in whatever information I can. So as I said, if you had 2 points on this line here, you can calculate the gradient, rise over run, and so you should be able to draw this line in accurately. But in this instance, we've just got everything's just A, B, C, D, E, so we don't know. Okay, finally here I've got, this is actually the graph of a modulus function, which used to be part of this course and was actually a really nice part of this course, but got removed a number of years ago. It's essentially a hybrid function, 2 linear graphs, and we've got this nice symmetry here so that we can see that we've got negative gradient on the left-hand side and positive gradient on the right-hand side, but in terms of the magnitude of the gradient, we've got that symmetry that's suggesting to us that it's the same sized gradient. So here we've got constant negative gradient. So in terms of drawing my gradient function, I'm going to have a constant negative value when x is less than 0. Again, we've got a sharp corner here, so my gradient graph won't exist at 0. And then I've got the same but positive gradient. So I want to make sure the distance either side of the axis is about the same. Okay, so I want to reflect that I can see that they're the same. And again, it's a positive constant gradient. So gradient undefined when x equals 0, so hollow circles, and then 2 horizontal lines indicating the constant gradient, but thinking about the fact that technically those horizontal lines should be about the same distance above and below the x-axis, given the symmetry that we're seeing in the shape. Okay, last one here. We've got a hybrid function. It has rule x squared minus 3x, so that is a parabola. Sorry, I've got it's the wrong way around. Sorry, can we swap? My apologies. Can we swap those rules in the definition? So this is 3x minus x squared, and this is x squared minus 3x down here. Okay, so we've got 3x minus x squared, which is a sad parabola with x-intercepts at 0 and 3, so that is that parabola. But we are only looking at that between 0 and 3, so that's where we're seeing this part up here. Okay. Then we are looking at the graph of x squared minus 3x, so happy parabola with x-intercepts at 0 and 3, so exactly the same graph actually, but reflected in the x-axis. But we only want that when x is less than 0 or when x is bigger than 0. So we only want this bit and this bit, okay? And so that's how we're getting this shape. The graphs are continuous at 0 and 3. They meet at that point, but obviously we've got sharp corners, so we're going to have issues with differentiability at that point. Okay, so part A, state the value or values of x for which f of x is continuous. Okay, so f of x is continuous for all the real numbers here. Okay, so we can draw the graph from start to finish without, and there is no finish, it continues on forever. We can draw the graph from start to finish without lifting our pen, so it's continuous for all real numbers. State the values of x for which f of x is differentiable. Okay, so it's differentiable for all the real numbers except for those 2 points where we've got those sharp corners. So except when x is 0 or when x is 3. So again, set notation, curly brackets. It's a list of specific values. It's not a range of values from 0 to 3. Then we want to find f dash x. Okay, let me just write f of x down here so that we can see it on screen. So f of x, now I fixed it, so it's 3x minus x squared. When x is between 0 and 3 inclusive, okay, and it is x squared minus 3x when x is less than 0 or when x is bigger than 3. Okay, so the derivative is going to be, so we can differentiate this. Now, I'm going to do the derivatives by rule in the next video, but I suspect that most of you recall well enough your patterns of differentiation from last year to know that 3x minus x squared, the derivative is 3 minus 2x. And here the derivative will be 2x minus 3. Now, the place we need to be careful here is over here, okay? Because thinking about the domain for our derivative function, it doesn't include 0 and 3. So therefore, it is the graph of 3 minus 2x when x is between 0 and 3, but not at 0 and not at 3, because they are cusps and therefore gradients not defined there, so the derivative function is not defined there. And there's no issues in the second branch, the domain there. So 2x minus 3 when x is less than 0 or when x is bigger than 3. So being really clear about, that's the main thing that you're going to need to be a bit careful about, adjusting the domain of your derivative function. Sketch the graph on the axis in A. Okay, so we're drawing the graph of 3 minus 2x, so it's an actual equation. It's not a rough sketch here. We know we can draw the line 3 minus 2x. It has a y-intercept at 3 and an x-intercept at 3 on 2. So y-intercept at 3, which is not included, and x-intercept at 3 on 2, and then obviously, when x equals 3, it's a not included point, but it will be 3 minus 6, it'll be at negative 3. Okay, so 3, negative 3, not included point again. So sketching a graph, intercepts, endpoints, they should all be marked with coordinates. Apologies, it's picking up my hand rubbing, dragging along the screen. Okay, so 0, 3, and 3, negative 3, and 3 on 2, 0. So those bits need to be marked. So that is the first branch, that is the line 3 minus 2x only between 0 and 3. And then we're going to have the line 2x minus 3, which is this exact same line but reflected in the y-axis. So it's exactly the same line, but we don't want the bits, we only want to draw that back here and up here. Okay, so starting at 3, and it'll be at 3, 3. It's going to have, okay, so we've got 0, negative 3 there, and 3, positive 3 there. All intercepts, all endpoints, all labelled and marked, and the graph nice and accurately drawn. Okay, so the work for today is from a mixture of exercises covering the concepts of continuity, differentiability, and graphs of gradient functions. I'd prefer that you do the work on continuity and differentiability before the graphs of gradient functions, just so you're thinking carefully about the domain of your gradient function when you draw it, and that is going to be equal to the set of values where the function is differentiable.